To begin the chapter on spontaneity, entropy, and free energy, we are first going to discuss what a spontaneous process is. Now, a spontaneous process is a process that occurs without any outside intervention. So you don't have to add anything to this particular reaction or phase change or what have you without, it can just occur on its own. They can be fast or slow, so there's a kinetics factor involved in a reaction that determines how fast or how slow the reaction is. Spontaneity is not how fast or how slow, but just simply whether the reaction actually goes. Now, many combustion reactions are very fast, but many combustion reactions are not necessarily spontaneous. There are combustion reactions that are spontaneous, and they are also very quick. Converting diamond to graphite or graphite to diamond is a very slow process, but it happens to be a spontaneous process. Now, how do we determine spontaneity? We look at several things, actually. We look at entropy and we look at enthalpy. Now, we've discussed the idea of enthalpy already, that is the change in energy. And most exothermic reactions, that is where there's heat lost, most reactions that are exothermic happen to be spontaneous. There is another factor involved in spontaneity, and this factor is entropy, and it actually helps to explain why some endothermic reactions are spontaneous. Now, entropy is simply a measure of the randomness or disorder of a system, and a spontaneous reaction generally is a reaction in which there is an increase in the entropy. So generally, a reaction that goes towards greater disorder is spontaneous. For example, a salt dissolving in water. Salt itself is very ordered and not very random in the crystalline structure, and then once it goes into the water, it's able to dissolve, dissociate, and occupy any number of places within the water, and so it becomes much more random as a solution than it is as a solid. So that would be an increase in entropy. Entropy then basically describes the number of arrangements that are available to a system. The greater the number of arrangements, then generally the greater the entropy. So a stack of cards sitting on a desk or on a table, not very entropic. Take that deck of cards and throw it up into the air, and do your 52 pickup, and you suddenly have a very entropic situation. Nature, there's a natural tendency towards the states that have the highest probability of existing, and that is the greatest entropy. So more disordered, random situations are generally favored. So we need to look at something called positional entropy then for that reason. Positional entropy is the probability of occurrence of a particular state depending on the number of ways in which that arrangement can be achieved. So what that means then is a solid is not very entropic because it's very ordered, and then a liquid is more entropic because there's a greater number of positions because the structure is a little less rigid. And then finally a gas, of course, is the most entropic of all three of the states of matter, because in a gas you can have those particles, those molecules, in any number of different, almost infinite number of arrangements. Now, we treat entropy in much the same way that we treat delta H. You can actually calculate the entropy of a reaction by taking the sum of the products, of course using the moles, minus the sum of the reactants, again using the moles. So you can actually determine, just as we did with delta H using heat of formation, we can determine the overall entropy change in a reaction by just looking at the products versus the reactants. So you would then look up the entropy values for the products in the reaction, look up the entropy values for the reactants in the reaction, and then simply subtract them. And then in general, as you begin to look at entropy, you will find the more complex the molecule, generally the higher the entropy. And of course this goes back to the more complex the molecule, the greater number of electrons, the greater number of positions those electrons can take up. So a starch molecule, which is just a huge carbon, hydrogen, oxygen molecule, would have higher entropy than methane, which is just simply CH4. So in general, the more complex the molecule, the higher the standard entropy.